the next class, we will be looking at many, many different algorithms in this fold. And in fact, local search is sort of very intuitive. So you can start making your own algorithms, and most likely either somebody has made it or there is some problem where this is helpful. So, just think about it that way. So, what is a possible problem with sideways move? Like an immediate problem, yes. Moving in wrong direction, that is problem with the whole of local search, right? I don't know whether we can fix it unless we have additional information. Yes. Algorithm might not terminate. Why might it not terminate? It's just going on and on looking at the same state. Let's say from state A I can reach state B, and from state B I can reach state A, and both of them have the same value, and suppose I don't impose a length of 100 limit, then what would happen? It will keep doing A, B, A, B, A, B, A, B. But it doesn't have to be. Suppose A goes to B, C and D, B goes to C, D and E, D goes to, and so on. There is this fully connected kind of a shoulder. What's going to happen? I'll keep just oscillating among these states. What's a simple fix? Limit on number of moves, sure, that's a simple fix that we have already tried to add in sideways move, right? So limit the maximum number of sideways moves. What else? One at a time, yes. Keep a track of the last node and keep a track of the last node and don't repeat it. What's your name? Shreya. Shreya says keep a track of the last node and don't repeat it, right? Now last node is a specific example. Up until now, we had complete amnesia. We had no idea where we came from. So what Shreya suggests, let's have a little idea where we came from. Let's remember the last node. We can generalize it to last k nodes, whatever. Right? And so this algorithm is called taboo search. And this spelling is not a mistake. I mean, this is just how the algorithm is called. So you create a taboo list, and taboo list is a fixed length queue. It basically says these were the nodes that were visited recently. Let's say the last 100, right? And you basically say you are not allowed to go back to the same node that is already in my taboo list. That's it. So add most recent state to the queue, drop the oldest. Never make the step that is currently tabooed. Now if you think about it, as the size of the taboo list grows, as you have a huge size of the taboo list, almost the full search space size of the taboo list, then you are essentially doing a systematic search. You are saying don't repeat a state, no redundancy whatsoever, don't repeat a state, look at all possible states that way. So eventually this will become systematic search if my taboo list becomes extremely large. But in practice, people use a small constant size taboo list, and that is about 100 or so. Now we can extend this idea. Why do we need a constant size taboo list? Let us say that we will keep exploring until we hit a better optimum. So that particular algorithm is called enforced hill climbing. The idea enforced means I am enforcing that I will always climb the hill. What does that even mean? So it means that I hit a local optimum, I start doing breadth first search. So now notice what are we doing? From a point of complete amnesia that I don't have any memory of where I came from, I am starting to add some memory in the system. Right? Initially I added a taboo list, which is a small memory, and now I am saying let us start doing breadth first search. Let us start doing systematic search. So I am doing hill climbing, I do hill climbing, I do hill climbing, I reach a local optimum. From that local optimum, I start doing breadth first search in all directions. I keep doing this breadth first search. What is going to happen is that at some point, if I do this breadth first search long enough, I will hit a state whose value is better than the root. Let's think about why that is going to happen. That's going to happen, let's say I am stuck in this second local optimum, right? So this particular local optimum. Or let's say I am stuck in this flat local optimum. third local optimum. Now, if I start doing breadth first search from here, I will be exploring states in all directions. So at some point, I will keep going, and eventually hit this node on the second hill, whose value will be better than me, and then I will jump. And then I will forget breadth first search and start doing hill climbing all over again. So I have enforced that if I am stuck in a local optimum, I am enforcing that you have to jump off of it. And this algorithm is called enforced hill climbing. In practice, what happens is that their exhaustive search is exhausting. It takes a lot of memory, it takes a lot of time. So in practice, what ends up happening is that I am spending a lot of time doing breadth first search. And then suddenly I have found a better solution. I jump and I start doing hill climbing. I quickly go up the hill for hill climbing, and then I'm stuck. And as soon as I'm stuck, I start doing breadth first search again, and there is a prolonged period of breadth first search before I get to the next optimum. This is, you can think of it as a middle ground between local search and systematic search. In systematic search, the search space will become so large that you will not be able to make progress, and the memory requirements will be very high. In local search, memory requirement is nothing. There is no memory requirement in practice. But I may not lead to an optimal solution. And so there is a middle ground here where I will do local search, then I will do systematic search, then I get to a better local point, I do local search, then I get to systematic search, then I get to a better local point, and I keep doing this. And this is a better middle ground where I will improve my solution, but I will not be using a full memory and time as a typical systematic search solution will be taking. And this algorithm was the algorithm of choice for a very well-known AI planner called the FF planner. FF was a planning system where the idea was to reach a start state to the goal state, and output would be a path. Now the output is a path. How can I do local search? Well, I will be searching in the path space now. I will be making local moves in the path space. I will be removing one edge and adding another edge, kind of a local move to my path. Each state will be a full path. And then on top of this, I will do local search, but I will be stuck in lots of local optima. There were lots of local optima, and so they came up with the enforced hill climbing algorithm, and that enforced hill climbing algorithm led to the best winning planner. By the way, this idea that assignment should be competitions is very, very common in the field of AI. Pretty much all fields have competitions. All the research communities in that particular field participate their software in those competitions. And whoever wins, their technology becomes more famous. So if you want to make an impact in any field, look at what competitions they participated in and try to win those competitions. For example, I worked in planning, so we also submitted some probabilistic planners in the past. And we couldn't win, but we were close second. So, we had some influential papers in early 2010s on probabilistic planning. The most famous planner for deterministic planning, not probabilistic, where the solution is a path, there is no probability, was the FF planner in the early 2000s. Right from about 2001 to up to about 2010-11, FF planner from Jörg Hoffmann, he is now at, I believe, Max Planck in Saarbrücken in Germany, was the planner that everybody used to try to compete against. And it was using enforced hill climbing local search algorithm. Yes, question. Very good question. The question is, when you reach the global maximum, you will keep doing breadth first search and you will never find a solution. So what do? At some point you will just say, okay, I am done with my time, I am done with my memory, I can't search any further, so this is the solution I am going to return. So in practice, do you know when to stop local search now that you are doing so many variations of this? It will never be clear. The best setting in which local search performs is I give you 2 minutes of time and your job is to come up with the best solution. So your goal is not to think about when to terminate, your goal is to say how do I use those 2 minutes most effectively. And that is where local search shines. Because you can just search and you can do some tricks and search further, do depth first search, search local search further, and before your 2 minutes are up, you output the best solution found so far. The best optimum found so far. Okay? But yes, we have not discussed very much on termination condition. In fact, what we do next will completely take away termination conditions. So let's see what we can do next. Now let us, up until now, we have been doing mostly deterministic versions of local search. There was a very little source of uncertainty which was in tie breaking, but modulo that, we were always choosing to go greedy and no non-determinism, no probabilities, no uncertainty. Now very early in the class we discussed two algorithms which were asymptotically complete. Local search, greedy local search on the other hand is not complete. It may be stuck in local optimum. What were the two algorithms, trivial algorithms that we did which were asymptotically complete? Those trivial algorithms were random sampling and random walk. Random sampling basically said, give me a new state, give me a new state, give me a new state randomly. And we discussed that eventually it may hit the optimum. Random walk, however, said, let's just randomly move in the neighbors without thinking about the objective function. And even that was guaranteed to hit the optimum eventually if the search space is connected. So these algorithms were asymptotically complete, but they didn't have the right intuitions of greedy search, hill climbing. Greedy hill climbing, on the other hand, is not asymptotically complete. So can I come up with some hybrid which is both asymptotically complete and has similar properties as greedy local search? These would be called stochastic hill climbing algorithms. The goal is to avoid getting stuck in local optimum. What do you think we can do? Any suggestions? Yes, what's your name? Prashant. Yes, Prashant. Whenever we are stuck in local optimum, randomly sample a new neighbor or a new state. Very simple. Whenever I am stuck in a local optimum, randomly sample a new neighbor. If I say this, what am I merging? I am merging greedy local search with random sampling or random walk. So again, if I am stuck, randomly sample a new neighbor. Randomly sample from one of the neighbors. Is this random walk or random sampling? Random walk. On the other hand, if I say, whenever you are stuck, randomly jump to a new state, this would be random sampling. So we can try to add, or both, we can try to add ideas of randomness in hill climbing. So we can do random walk hill climbing, or random restart hill climbing, or hill climbing with random restart and random walk. Right? The algorithms are not deep at all. In fact, if you had thought of it for 2 minutes, you may have been able to come up with them. Very simple ideas. So the idea is that whenever state space landscape have local optimum, any search that moves only in the greedy direction cannot be complete. Random walk is asymptotically complete. So let us put random walk into greedy hill climbing. So let us do very simple. We can do what Prashant said, or the nicer version of that is, with probability P, move to a greedy neighbor, with probability 1 minus P, move to a random neighbor. And for now we are keeping this probability P constant. But ideally, what do you want? Should P change over time, and if P should change, should it increase or should it decrease? It should increase. So as time goes on, I should take more and more greedy steps and less non-greedy steps. Initially it is okay to take many more non-greedy steps. Why? Because I may have started in a bad hill and I may need to jump off that bad hill slowly. And that changing of probability over time is called, one way of doing this is called simulated annealing, which we will come to just in 2 minutes. Yes.
When you are studying the
Right. So the question is, why are we doing it at every step and not at the local optimum? And that's a fair question. See, main issue is that if you are stuck at the local optimum, getting off that local optimum is harder because it requires you to take lots of suboptimal moves again and again and again. So therefore, these algorithms suggest that you should start taking suboptimal moves at every step just in case you mix well. So now there are many algorithms that we will study, but if you have to remember only one of them, like absolutely only one algorithm you want to take back from this class. Now, people will disagree with me, but this is my personal choice. It would be this algorithm. Hill climbing with random restarts. And probably this is the way you would have thought I should fix hill climbing in the first place. Do hill climbing, get stuck at a local optimum, then randomly sample a new state and do hill climbing again. And then randomly sample a new state and then do hill climbing again, and always keep the best solution found so far. The idea is, if at first you don't succeed, try again. That's it. So for each restart, now there are choices, right? So there are lots of parameters in all these algorithms. So one parameter here is, for each restart, do you go up to greedy optimum, or you stop in the middle and then restart? Okay, that's a choice. How many restarts do you do? Do you do a fixed number of restarts, or do you run indefinitely? Now that's not really a choice. That depends on the total amount of time that is given to you. And you can also do some analysis. And given the interest of time, I will let you figure out this analysis. But suppose each search has a probability P of success. How many restarts would I need to do in order to hit a solution expected? How many expected number of restarts I will have to do? Right? This is math 101 for college. It would be 1 by P, and you can figure out why. Right? So if 8 queen succeeds 14% of the time, and I am doing a random starting point every time in an expected number of 7 restarts, that means 6 into 3, 18 plus 4, 22 hill climbing steps, I will hit my solution in an expected sense. And as I said, if you want to pick one local search algorithm to start with, if you are given a new problem, always you have to start define your state space, you have to define your neighborhood function, you have to define your evaluation function, you have to define a random function which will give you a new start state, random start state, or a possibly good random start state. But once you have done that, the first algorithm I suggest you implement is hill climbing with random restarts, and fine tune some parameters to figure out whether it gives you a good enough solution or not. Of course, you can do both. So you can do hill climbing with both random walk and random restart. So at each step, do one of the three. Either take a greedy move with some probability, or you take a random walk move to a random neighbor with some probability, or you do random restart, resample a new current state. And a better algorithm which does this random walk with a slowly changing probability schedule is called simulated annealing, but in the interest of time, we will start from here in the next class. Okay? So we will start from simulated annealing in the next class. We will then go to local beam search and its variations, and one of the significant variation there is genetic algorithms, which we will study in the next class. After that, our local search will be done, and we will start with game playing as our topic next week. Okay? Let's stop here.